Hello and welcome back to the discussion. So, we will continue our discussion on the materials, engineering materials and their properties. So, we have discussed so far the true stress, true strain, and that we have compared with the engineering stress, engineering strain, and we said that the true stress and the true strain is more realistic in one word, because there what is considered is not the initial area, but the area which is going through the stress or the initial elongation which has been taken finally. So, that elongation is taken in the case of the true strain. Now, in the flow curve, if you see here, once again I am repeating that this is the relationship between the true stress and the true strain through the strain hardening, and we said that strain hardening is the ability of the material to withstand the increased load despite the uniform reduction in the cross sectional area. So, this is the equation which is normally called the flow curve in the engineering, okay. And here the K is the strength coefficient in megapascal, and the strength coefficient means that this is the constant, this is the coefficient which actually defines the strength of the materials, okay. Next is the categories of the stress strain relationship. There are basically the three categories that we can identify. One is the perfectly elastic, elastic and perfectly plastic. Third category is the elastic and strain hardening. By these categories we mean to say is that if we take the stress strain relationship of a ductile material. So, in here as you understand that we have distinct three regions, okay. Perfectly elastic region, then we have elastic and plastic, a small region, and then we have elastic and the strain hardening, all right, here within this. All right, let us see perfectly plastic. Now, this is a straight line when the stress is proportional to strain, behavior is defined completely by modulus of elasticity, okay. It fractures rather than yielding to plastic flow. It fractures here, then it will not yield and it will not demonstrate the plastic flow, as in case of the brittle material, all right. Now, brittle materials, ceramics, many cast irons, thermosetting polymers, these are the materials which actually demonstrate this kind of a curve, okay. This is called the perfectly elastic category of the stress strain relationship. So, this is no more for the plastic material or for the ductile material, but this is for the materials like ceramics, cast irons, okay, thermosetting polymers and so on. Second is the elastic and perfectly plastic. This is elastic and perfectly plastic. Stiffness is defined by E, okay. This is, as we said, that modulus of elasticity. Once Y reached, that means this point reached, deforms plastically here at same stress level, okay. The stress level is not changing, at the same stress level it is actually plastically deformed, okay. Therefore, the flow curve is K is equal to Y, because there is no strain hardening here, N is equal to 0, and therefore, in the flow curve will be K is equal to Y, okay. If you see the flow curve that we have shown, that here, all right, Y by mean to say that we are defining that as an Y. So, therefore, we are saying as an Y. Metals, well, we mean to say that this is the yield point, by the way, all right. Now, the metals behave like this when heated to sufficiently high temperatures. When the metal is at sufficiently high temperature and then the stress is applied, though the stress strain curve will be this way, that it will be initially it will be elastic and then it will be plastic without the plastic region starts without any stress being increased. So, the same stress level. That means, the temperature of heating should be above the temperature of recrystallization. Okay. Elastic and the strain hardening, that is the third category. Then the Hooke's law in elastic region yields at y. Okay. So, flow curve in this case will be k is more than y, because n is positive, n is more than 0, meaning that the strain hardening occurs. All right. Most ductile metals behave this way when cold worked without heating the material. When the stress is applied, so then the stress strain curve will be similar to what is shown here in this picture. So, this is the third category, that is elastic and the strain hardening. Now, I would like to repeat once again that these are the categories depending on the material. Okay. Depending on the material, we can have the stress strain curve which is perfectly elastic. Depending on the, for example, it is for the brittle materials. Depending on the material, we can have the elastic and perfectly plastic material behavior. Okay. When the material is heated above the temperature of recrystallization, or we can have the elastic and the strain hardening, which is the case of most of the ductile materials when they are cold worked without heating the material. Okay. Typical values of the K and the N. K is the strength constant or the strength coefficient, N is the strain hardening. All right. These are the values you can see. This is for your comprehension, that depending on the material, we can have the different strength coefficient as well as the different strain hardening exponent. Okay. So, the flow curve will be different. You can find out the flow curve for each of these materials when the stress strain relationship has been made. Okay. So, if you have the testing and you are measuring the strain for the stress, so for the applied stress, in that case you can find out what will be the flow curve, knowing the strength coefficient and the strain hardening exponent. Okay. This is by this table, that is the outcome that you can get actually. Now, let us see what is the compression test. Applies a load that squeezes the ends of a cylindrical specimen between the two platens. Let us say here there is a plate, this is the specimen, and there is a plate here, there is a plate here, and if we actually put this load like as it is shown in this direction, this will be compressed, meaning that the height of this specimen, it will be reduced from h0 to h, okay, because of the applied load, as you can see. However, the diameter or the cross sectional area can be increased. As you can see from here, this is the cross sectional area of this initially before applying the load, and after the load is applied, the compression happens, and it reduces in the specimen reduces in length, and it is increased in the diameter. It is normal thing, many of you might be knowing that. Okay. Engineering stress in compression. So, engineering stress, as the specimen is compressed, its height is reduced and cross sectional area is increased. So, then the engineering stress will be F divided by A0. A0 is the original area of the specimen. See, the difference is, I mean the thing is that here it is the still original area, all right, which is here. Engineering strain in compression will be E is equal to H minus H0 divided by H0. So, H and H0 are this. H is after the compressive forces are applied, and H0 is the initial length, all right. So, it is still the initial length that we are using, because it is the engineering stress and the engineering strain. Since height is reduced during the compression, value of E is negative. The negative sign is usually ignored when expressing the compression strain. By negative, we mean that this is the height is reduced, but it is not written here actually. I mean, when you get the value, it will be negative value, that means it is a compression. That is what it means. Shape of plastic region is different from tensile test because cross section increases. Okay. You understand that we said this, the diameter is increasing, height is decreasing. So, therefore, the shape of the plastic region here, this will be different. Since the load increases more rapidly, than previously, the calculated value of engineering stress is higher. Okay. This is to be understood that the load increases rapidly. So, therefore, as you calculate the value of the engineering stress, it will be obviously higher. Okay. This is typical engineering stress strain curve, stress versus strain, but this is the engineering stress strain. Okay. That is for the compression test. Tensile test versus the compression test. So, we have seen that compression test, now it is a tensile test. Although differences exist between engineering stress strain curves in tension and compression, the true stress strain relationship are nearly identical. Okay. So, here this is another factor, this is very important and very unique, because here the true strain and the stress relationship will be the same in case of the tension and compression. Since tensile test results are more common, flow curve values, that is the K and the N, strength coefficient and the strain hardening from tensile test data can be applied to compression operation. This is understood. When using tensile K and N data for compression, ignore necking, which is a phenomena peculiar to straining induced by tensile stresses. Now, once again I will repeat that when using tensile K and N data for compression, okay, these are the data obtained by the tensile test, and when it is used for the compression, ignore necking, which is a phenomena peculiar to the straining induced by the tensile stresses, because here that means you have to ignore, because you have that necking will be particularly for this situation and not for the compression. All right. These are the recommendations when you are comparing the tensile test and the compression test results. Okay. Testing of brittle materials, how to do that? As we said that the stress strain curve is such that it does not go beyond the yield point. Okay. So, it does not yield actually, does not go beyond the elastic limit actually. Hard brittle materials, for example ceramics, possesses elasticity, but little or no plasticity. Okay. Often tested by a bending test, also called the flex check test. So, it is subjected to a bending force, okay, and the bending moment is seen or measured. Specimen of rectangular cross section is positioned between the two supports, and a load is applied at its center, okay, and the bending is measured. For example, it is like this in this figure given. So, this is the brittle material, okay, testing of brittle materials. This is the cross section and here is the load given. So, that load will actually bend this, okay, compressive stress and the strain here, and the opposite side it will be the tensile stresses and the strains. All right. Now, bending of a rectangular cross section results in both tensile and the compressive stresses, as it is shown here. As it is applied from here, from the top, on the top once again I am repeating that this will be the compressive stresses and strains, whereas on the opposite side it will be the tensile stresses. This is obvious. Okay. This is the initial loading, highly stressed and strained specimen and the bent part as the force is removed. Okay. Testing of brittle materials continuing. The brittle materials do not flex, all right. They deform elastically until fracture. Failure occurs because tensile strength of outer fibers of specimen are exceeded. Failure type can be called the cleavage, common with ceramics and metals at low temperatures, in which the separation rather than the slip occurs along the certain crystallographic planes. Now, the slip is the plastic deformation. Slip occurs when the plastic deformation occurs and along the slip line. Okay. Now, here it is a separation. So, that is why the failure is called the cleavage. All right. This is commonly applied for the ceramics and the metals at low temperatures. Transverse rupture strength. The strength value derived from the bending test is this. So, this is called the transverse rupture strength. This is equal to 1.5 F into L divided by BT square. Okay. So, F is that applied load, this is the F, and L is the length of the specimen, this is the length from here to here, okay. And B and T, as you can see from here, this is the B and this is the T in the cross section, you can see this. So, this will be divided by the B into T square. This value is equal to the transverse rupture strength, all right, and this is measured in the or expressed in the megapascal. Okay. Shear properties. Now, the application of stresses in opposite directions on either side of a thin element. So, this is, let us say this, suppose this is a thin element and some stresses are applied, let us say this is the shear force. So, this will apply the shear stress on this initial material and the material will be deformed in this way, okay, where this is the, let us say, height and this much is the deformed part, okay. This is the deformation that has occurred. Now, this is the shear properties with the shear stress defined as the F divided by A, okay. F is that applied force, but earlier it was the normal force, okay. Here we are having the shear force. So, these forces, since it is creating the shear stress, these forces are called the shear forces, and A is the area over which the deflection occurs, okay. Now, the shear strain accordingly defined by the delta divided by B, and the B is, as I said, the distance between the two layers, okay. If we consider this layer is moving with respect to this layer in the opposite direction, so the distance between these two layers will be, let us say, B, and deflection of the element is the delta. So, delta by B will be the shear strain, all right. This shear strain we will actually find out during the metal cutting, because in metal cutting, as you understand, that the shear strain is very important phenomenon. There the high strain rate of deformation, okay, occurs, and that is because of the shear stress, okay, applied and the shear strain applied to the workpiece. Now, this is the typical shear stress strain curve from a torsion test, okay. Now, in the plastic region in here, the material strain hardens to cause the applied torque to continue to increase until the fracture occurs, okay. Now, the material strain hardens and this causes the applied torque to continue to increase, all right, and then the fracture occurs at some point of time when it is segregated, the material is segregated from the actual base material. So, this is the shear strength, all right. This point is defined as the shear strength, and here it will be this, along this axis it is the shear stress, along this axis is the shear strain, all right. Shear elastic stress strain relationship is in the elastic region, the relationship is defined as shear stress is equal to G into the strain, okay. This is the shear modulus. So, this is proportional to the elastic shear stress is proportional to shear strain, and this is equal to constant into the shear strain, and this constant is called the shear modulus, okay, because it is a shear stress and it is the shear strain, all right. For most materials, this G is equal to 40% of the elastic modulus, okay, that is about 0.4 into the elastic modulus. So, this is not the same as the elastic modulus, but it is only the 40% of that value, and this is the shear modulus. So, therefore, shear modulus and elastic modulus, they are different, okay. As you can see that elastic modulus is more than the shear modulus. Shear modulus is only 40% of that, 0.4. Shear plastic stress strain relationship similar to flow curve relationship, shear stress at fracture is equal to the shear strength. Okay. So, that is what we said here, this is equal to the shear strength, all right. Shear strength can be estimated from tensile strength, which is about 70% of the tensile. Okay. This is how you can find out that what is the shear strength, which is about 70% of the tensile stress. Now, since cross sectional area of test specimen in the torsion test does not change as in case of tensile and compression, engineering stress strain curve for shear is equal to true stress strain curve. This is the reason, if you remember, we said that in the beginning that the engineering stress strain curve for shear and the compression, that remains the same because of this reason, since cross sectional area of the test specimen in the torsion test does not change as in case of the tensile and the compression. Okay. So, therefore, these two are the same here in this case. Let us see what is hardness, is the resistance to permanent indentation. So, it does not allow, the hardness does not allow the indentation so easily. Okay. Good hardness generally means the material is resistant to scratching and the wear. That is what is desirable for the engineering parts, that it cannot be scratched or the wearing action will be wear of the material will be, should be low, wear and tear should be low, particularly in case of the tools, metal cutting tools, right. Most tooling used in manufacturing must be hard for scratch and wear resistance. As I was telling, that there should be less wear, so that the tool life could be very high, that we will discuss in the machining. Hardness test commonly used for assessing the material properties, okay, because they are normally quick and the convenient, and you can quickly find out what is the hardness of a particular material, and that is required because this is the property we always use, that what is the hardness, depending on that we are going to use it for a certain combination of work and the tool, for example in machining. Variety of testing methods are appropriate due to difference in the hardness among the different materials. All right. Most well known, of course, is the Brinell and the Rockwell, that I have already told you, that the Brinell hardness or the Rockwell hardness is what we use to define the hardness of a particular material. Okay. So, this can be HRC, HB, if you remember. So, that is the Rockwell is the HRC, Brinell is the HB, and so on. Other test methods are also available, such as Vickers, Knoop, scleroscope and the durometer. All right. So, along with the Brinell and Rockwell hardness, there are other tests, okay, other test methods which are Vickers test, Knoop test, scleroscope and the durometer. These are the instruments by which the hardness of a material can be measured. Now, the Brinell hardness, for example, how it can be done, this is a 10 millimeter ball. So, this is a standard procedure that all over the world the Brinell hardness is measured by this, whatever is the material specimen material is, that this is the 10 millimeter ball, and that material should be of steel or cemented carbide, okay, and the diameter has to be the 10 millimeter, and this will be the indenter, meaning that a force, this ball is placed on the specimen and a force is applied on the ball, so that the ball makes an indentation here. Okay. So, the shape of the indentation will be semicircular like this, and this is the diameter di on the specimen. Here, as you can see, that this is the di on the specimen, this is measured after the force is removed and this ball is removed. So, this is how the Brinell hardness is tested. Okay. The widely used for testing metals and non-metals of low to medium hardness normally. Now, this ball is of course the hard ball, and that is pressed against the specimen surface. Load is normally, the F load is normally 500, 1500 or 3000 kilogram. All right. Now, the hardness will be expressed, this does mean, because does mean much, because for 500 it is something, for 1500 it is something, for 3000 it is something else, all right. So, it has to be mentioned that these are the parameters which have been used in case of the testing, and if it is a standard testing, then of course, a certain value will be used and that has to be specified. Okay. Brinell hardness number is load divided into the indentation area. This is the Brinell hardness number. Okay. This is how it is defined, that is 2 into F. Now, here you can see that the F will be then determined, all right. Either it is 500 or 1500 or 3000. This may not be mentioned because HB, the Brinell hardness number itself, says that this has been taken care of. Okay. So, pi into dB, okay, dB is the diameter of the ball and di is the diameter of the indentation as we have shown it. So, this will be 2f divided by pi into dB minus root over dB square minus di square. All right. So, this will be the value that is given for that particular material for which the Brinell hardness has to be specified. Rockwell hardness test similarly. This is another widely used test. Here in this case, a cone shaped indenter is pressed into the specimen. In case of Brinell, once again this is the hard ball is used as an indenter, and here it is a cone shaped indenter which is used as an indenter which is pressed into the specimen using a minor load, and that load is about 10 kilogram. In case of Brinell it was 500, 3000 and 1500 and 3000. Okay. Thus, sitting indenter in material, all right. Then a major load of 150 kilogram is applied. So, first we will put that so that there is an indentation, small indentation, so that it could sit in the material, and then a major load will be of 150 kilogram on the same indenter is applied, causing the indenter to penetrate beyond its initial value. Okay. Additional penetration distance d is converted into a Rockwell hardness reading by the testing machine. Okay. So, once again here there is a cone shaped indenter, it is first pressed initially lightly. So, with a load of let us say 10 kilogram. So, when it has made an indentation, so it has made a mark. So, then the 150 kilogram of additional weight will be applied, so that the cone shaped indenter can go penetrate the material deeper way, okay, and that value is used by the testing machine to find out the Rockwell hardness reading. Okay. And as you understand, the Rockwell hardness will be different than the Brinell hardness, because the properties of or the method of measuring these two hardnesses are different. Here is in diagram it is shown that the cone shaped indenter will essentially have this is a standard cone which will have an angle of 120 degree, okay, and this is the initial position where we have given a small load of 10 kilograms, so that indentation is made, all right, and then the final load of 150 kilogram is applied, so that it goes farther. Okay. So, the difference between these two, initially it was this line, okay, then the final indentation is this. So, this value of d is used to define the used to find out the value of the Rockwell hardness, okay, and the machine will itself estimate that, and it will determine what will be the Rockwell hardness. Now, effect of temperature on properties, this is very important, because most of the engineering materials work to some extent at temperature more than or different than the ambient temperature. So, in case of in manufacturing, in the production particularly, the we are bothered about our tool materials, and which work at a very high temperature. So, therefore, what is the effect of the temperature on the properties of the material, that is very important to understand. let us say here it is the strength and ductility, we will put it on the y axis, okay, and the temperature we will put it on the x axis. So, tensile strength, yield strength and the ductility given in percentage of elongation, all right. Now, as you can see that these are the they behave differently as the temperature is increased. When the temperature is increased, the ductility goes up, all right. It goes up not linearly, but it is a non-linear curve, you can see that. Okay. Similarly, the tensile strength and the yield strength both fall as the temperature is increased. Okay. So, strength and ductility therefore, will be in the y axis as we said. So, yield strength and tensile strength both fall in as the temperature increases. Now, here you can see that all these three curves are non-linear, because the equation between the temperature and the tensile strength, yield strength and the ductility, okay, separately if you consider, then the equations, all three equations will be non-linear equation. Okay. Therefore, the this is not a straight line really, and neither is the ductility curve, but this is a major aspect that is should be understood, that tensile strength, yield strength, they fall as the decrease as the temperature increases, but the ductility increases. Okay. This is the gist of this curve. Now, hot hardness, ability of material to retain hardness at elevated temperature. I already defined the hot hardness definition. Now, the hot hardness, if you take the hardness here and at a higher temperature, as you can see that ceramic, this fall is not as rapid as for example, high alloy steel, or not as rapid as for example, low carbon, all right. See, for example, if it is 500 degree, even then the hardness is maintained, okay. But for 500 degree, in case of high alloy steel, the hardness drops drastically, okay. So, this means that the hot hardness of the ceramic is much more than any one of them, than the high alloy steel or high carbon steel or the low carbon steel. Okay. Now, the hot hardness, typical hardness as a function of temperature for several materials are shown here. Okay. These are the 4 different materials, and ceramic being the best as long as the hot hardness is concerned, and therefore, as I told you earlier also, that ceramic material is one that we normally used for when the high temperature is involved. So, at a high speed, for example, the cutting tool is used as a ceramic with ceramic material, because at high speed cutting, or the when the cutting speed is very high, the temperature becomes very high, and at that temperature the hardness of the tool material should not fall. Okay. So, hot hardness has to be more, has to be high. So, here you can see that for ceramic at 500 even the hardness is quite high. So, the hot hardness of ceramic is higher. Recrystallization in metals, most metals strain harden at room temperature according to the flow curve. Okay. So, if you see the most of the metals, all right, the N is more than 0, but if heated to sufficiently high temperature and deform, then the strain hardening does not occur. So, this phenomena is very interesting phenomena, that when at a sufficiently high temperature the metal is heated up and then deformed, then the strain hardening does not occur. Okay. Instead, the new grains are formed that are free of strains. Okay. Normally, the metal behaves as a perfectly plastic material. This is that strain hardening is 0, because it has been heated up to a sufficiently high temperature. All right. Recrystallization temperature, that is the formation of new strain free grains, that is called the recrystallization, meaning that when we say that the new grains are formed that are free of strain when the metal is heated up at a sufficiently high temperature, this will be at a temperature more than the temperature of recrystallization. That is what we said earlier. So, this is the recrystallization temperature. It is defined as when the formation of the new strain free grains, this is the recrystallization process, and the recrystallization temperature of a given metal, this is about 1/2 its melting point, 0.5 into the Tm. Tm is the melting point as measured on an absolute temperature scale. Okay. Now, recrystallization of course takes time. The recrystallization temperature is specified as the temperature at which new grains are formed in about 1 hour. Okay. So, that time is specified for during which this recrystallization process takes place and the new grains are formed. Okay. Recrystallization and manufacturing, how this recrystallization process is related or how it is important for the manufacturing is the recrystallization can be exploited in manufacturing. Okay. In which way? In the following way, that heating a metal to its recrystallization temperature prior to deformation allows to endure a greater amount of straining. This is very obvious because metal is being heated up prior to deform the material, okay, and lower forces and power are required to perform the process. Okay. Once again, as the metal is heated up to its recrystallization temperature or more than that prior to deformation, this will have the greater straining of the material and therefore, the less force and power will be required. See, this is an advantage for the manufacturing because we always are bothered about the power, okay, power of the machining. As the less power is consumed, it is better, less force is to be applied for removing the material, it is better, all right, because in that case the prime mover of the machine has to be can be of less powerful, okay, and this will be cheaper. So, therefore, in the machining these there is some research also going on that when during the cutting process the material is heated up, okay, and this is the reason why the material can be heated up before the chip is removed, because the forces and the power consumption during the process will be less, because the temperature the temperature at which the workpiece has been heated up, this may be crossing temperature of recrystallization. Only then of course, it will happen that N is equal to 0. Forming metals at temperatures above recrystallization temperature, this is the hot working. Hot working is very famous in particularly the metal forming, okay, because in metal forming it is important that the force required in the die and the forms these to be less. Okay. So, when it is worked in the hot working, then the hot working condition, then of course, the deformation easier, and metal forming it is advantageous, all right. Fluid properties and manufacturing. Okay. So, fluids they flow, that is one thing. They take the shape of the container that holds them, that we all know, and many manufacturing processes are accomplished on materials converted from solid to liquid by heating. Okay. Let us take some examples. Metals are cast in molten state, otherwise the casting process cannot take place. Glass is formed in a heated and highly fluid state. Okay. So, initially it is heated up, it is made in the molten state and then it is put in the forms, different kind of forms, so that the glass works can be manufactured. Polymers, for example, they are also almost always shaped as a thick fluid, almost always. There are some processes where polymers are used in the solid state. However, inside the machine it is actually melted. Melted means it is making in the thick fluid state. Okay. So, therefore, as you can see that for casting, for glass formation of glass utensils, for example, polymers, they are always in the fluidic state, all right. Therefore, let us see some of the properties of the fluids. Now, viscosity in fluids. Flow is a defining characteristics of fluid. Of course, it flows as we said, but the tendency to flow varies for different fluids obviously. Okay. Viscosity is the resistance to flow, that is characteristic of a given fluid. Okay. So, if the fluid is very thick, so you understand that it will flow not that easily, right, or if the viscosity is very high, okay, in that case high or low viscosity will flow in a different way, that is what we mean. If it is a thick fluid, it will flow less. If it is a fluid more fluidic, it will be flowing more rapidly. That is what it is being said. Viscosity is a measure of the internal friction when the velocity gradients are present in the fluid. Okay. The more viscous the fluid, the higher the internal friction and the greater the resistance to flow. That is what I just now said. More viscous material will have the more resistance, all right, to flow. And in the case of the viscous fluid, there will be more internal friction. That is why actually the resistance to flow will be more. That is another reason. And that is the reason. Reciprocal of viscosity is actually fluidity. So, more the viscosity, less will be the fluidity. Higher viscous fluids, they will not be flowing so easily as I was telling. So, there we express in an engineering term that the fluidity is less. The ease with which a fluid flows, that is the fluidity. Okay. So, more viscous fluids will have less fluidity and vice versa, less viscous fluids will have more fluidity, they will flow easily, as I was telling you just now. Viscosity can be defined using two parallel plates separated by a distance d. Let us say there are two plates, and this is the distance between them. Here we have a fluid which is flowing in between. Okay. This is the stationary plate and this is moving with respect to this stationary plate. Okay. A fluid fills the space between the two plates, as I was telling, and this will be the flow velocity vectors. Okay. This almost all of us know about it. We have seen it in many other fluid mechanics courses or other courses, all right, that when the within the fluid it will be flowing, the velocity is 0 here and the maximum here, and this is the flow velocity vectors. Okay. Slope is given by this is dy and this is the dv. Okay. So, this velocity is the v, this is the velocity of the moving plate. Shear stress is the frictional force exerted by the fluid per unit area. Now, the motion of the upper plate is resisted by a frictional force resulting from the shear velocity of the fluid. Okay. There is a shear velocity, and because of that there is a frictional force, and that frictional force resists the movement of the upper plate, which is moving at a velocity v. This force F can be reduced to a shear stress, let us say tau, by dividing by the plate area A. Let us say plate area is A. In that case, the F divided by A will be equal to the shear stress. So, this is how the shear stress can be defined, that this is the force divided by the plate area A, and the shear stress tau is given in the Pascal, okay, or Newton divided by meter square, Newton per meter square, which is expressed in Pascal. Okay. Sometimes we find that this is also given in megapascal, because the value of this stress is very high, and therefore, it is in the expressed in the megapascal. Same thing, Pascal or megapascal. In Pascal is expressed in terms of Newton per meter square. So, in that case the force is in Newton and area is in meter square, okay, obviously. Shear rate. Shear stress is related to shear rate, which is defined as the change in the velocity dV relative to the dy. So, if you see here, for example, dV here and dy here, okay, this is the change in the velocity with respect to the distance. All right, this is what we are saying, and this is the shear rate, because here the time will come into picture, because this is the shear rate, which is defined as the change in velocity dV relative to the dy. This is the shear rate. Okay, this is 1 by second, and because again I am telling you that this will have the time in picture, all right, because it is a rate. dV is the change in the velocity, the unit will be the same as the velocity, meter per second, and dy is the change in the distance, which is in meter. Okay. That distance y, how it is changing, where the change in the velocity is measured. So, this will be the slope, right, of that curve or of that line, okay. And that is given by the shear rate. Shear rate is the velocity gradient perpendicular to flow direction. This is how the shear rate can be defined. This is the same as the velocity gradient. You can see that this is the velocity gradient, change in the velocity with respect to the distance, all right. And this is perpendicular to the flow direction. Flow direction is in this way, and this is the change in the distance with respect to the flow direction, I mean perpendicular to the flow direction. Shear viscosity is the fluid property. This is one of the fluid properties that defines the relationship between the F by A, okay, and the dV by dy. That is F by A, this is actually the nu into dV by dy. See, this is the same as the shear stress, okay, and this is the same as the stress here, okay, shear rate. So, this is the shear and this is the shear rate, they are related by a constant of proportionality. This is called the coefficient of viscosity. Okay. So, once again the shear, this is the shear stress is proportional to the shear rate, okay, and this will be therefore equal to the constant of proportionality, which is the coefficient of viscosity, into the dV by dy. dV by dy is the shear rate. For Newtonian fluids, viscosity is a constant. Okay. When we talk about non-Newtonian or the Newtonian fluids, this is the viscosity that matters, that where the viscosity is constant, it is a Newtonian fluid, and for fluids where the viscosity is not constant, there those fluids are called the non-Newtonian fluids. Once again I am explaining that this we are discussing because in the manufacturing the role of the fluids is very high, particularly when we talk about the hydraulics. Okay. In the hydraulics we have the pipelines through which the water or any other fluid flows. So, we have to understand that what are the properties of such fluids, so that we can understand or design properly the hydraulic devices. That is why we need to understand the properties of this fluid. Coefficient of viscosity, rearranging coefficient of viscosity can be therefore expressed as this, okay, that is tau divided by shear rate. Viscosity of a fluid is the ratio of therefore shear stress to the shear rate during the flow. This is the viscosity of a fluid, this is a viscosity constant we said, okay, constant of proportionality, that is coefficient of viscosity. So, this defines the viscosity, that means we are saying that this is a ratio of the shear stress to the shear rate during the flow, when the fluid is flowing. Unit of viscosity is Newton second per meter square, okay. From here you can find out Newton second per meter square, and this can be expressed as a Pascal second, okay. This is the unit of viscosity. Viscosity of polymers and flow rate. Viscosity of a thermoplastic polymer melt is not constant, it is affected by the flow rate and its behavior is non-Newtonian, okay. There the viscosity does not remain constant. If you see this, the non-Newtonian, the viscosity is not constant, Now, you understand that this is thermoplastic polymer we are talking about, the melt is not constant, okay, the viscosity. A fluid that exhibits this decreasing viscosity with increasing shear rate, this is called pseudoplastic. Okay. This is the concept of the material, that is a pseudoplastic material, where their viscosity decreases with the increasing of the shear rate. Okay. This complicates analysis of polymer shaping processes such as injection molding. So, as you understand that the injection molding is directly related to the manufacturing, and here if we have the pseudoplastics, this will actually complicate. We have to take care of this property of the pseudoplastics, that the viscosity will be changing depending on the shear rate, and we have to know beforehand that how much viscosity can be changed with the applied shear rate. Then only you can have the process, that is the injection molding, properly designed. Okay. This is how it happens. Viscous behaviors of Newtonian and pseudoplastic fluids. Polymer melts exhibit pseudoplastic behavior. Okay. This is the one, this is the Newtonian, and this is non-Newtonian fluid, and this is the plastic solid. Okay. Behavior of a, for comparison, the behavior of the plastic material is given. This is the plastic material, this is the pseudoplastic fluid, okay, which is non-Newtonian, because the Newtonian fluid will behave this way, and this is the yield stress, this much, because this is in the shear stress and the shear rate, tau, and the shear rate. Okay. Viscoelastic behavior, material property that determines the strain it experiences when subjected to combination of stress and temperature over time. Okay. So, this is a combination of viscosity and elasticity, this is the concept here. Once again, that determines the strain it experiences when subjected to combination of stress and temperature over time. Okay. So, this is the combination of viscosity and the elasticity, therefore, we are saying. If you see here comparison of elastic and the viscoelastic properties, here we have the stress, here we have the time, okay, and in this here it is a perfectly elastic response of a material to stress that is applied over time. Okay. Here the response of a viscoelastic material, okay, under the same condition. The material in B here takes a strain that is a function of time and temperature, you can see from here. Okay. Now, viscoelastic behavior of polymers, very important phenomena and very important property that is being used very widely for in the manufacturing and in many other industries. This is called the shape memory. Okay. Now, a common problem in extrusion of polymers is the die swell. Okay. Die swell, in which the profile of extruded material grows in size, reflecting its tendency to return to its previously larger cross section in the extruder barrel immediately before being squeezed through the smaller die opening. See, if you remember, these are the defects, some of the, we call it some of the defects in case of the extrusion of the materials, and we have to take care of this. So, this is what happens, that means the material remembers the previous shape. Okay. So, when it goes through this smaller cross section, it remembers the earlier volume or the cross section, and it immediately comes back, immediately it wants to come back to the initial shape. So, that is called the shape memory. Okay. Physical properties of the material, continuing, that volumetric and the melting properties, okay, thermal properties. These are the two categories that the physical properties of materials in physical properties of material can be considered. Physical properties define properties that define the behavior of materials in response to physical forces other than the mechanical. This includes the volumetric, thermal, electrical and electrochemical properties. All right. Now, components in a product must do more than simply withstand the mechanical stresses, that is one thing. They must conduct electricity, okay, to prevent conduction, either they conduct electricity or they prevent the conduction, allow heat to transfer or allow it to escape, transmit light or block the transmission, right, and satisfy many other functions similarly. Physical properties in manufacturing, important in manufacturing because they often influence the process performance. I have given you of course enough examples in between that why these properties are important for the manufacturing. Examples, other examples additionally. In machining, for example, the thermal properties of the work material determine the cutting temperature, right, which affects how long tools can be used before failure. All right. In microelectronics, for example, electrical properties of silicon and how these properties can be altered by chemical and physical processes is the basis of semiconductor manufacturing. Okay. So, while manufacturing, either it is a manufacturing of semiconductor, now the or it is the cutting process, for example machining, there all these physical properties are important. Volumetric and melting properties. Properties related to the volume of solids and how the properties are affected by temperature. That includes of course density, thermal expansion, melting point. All right. Density is defined weight per unit volume, and that you all know that this is the gram per centimeter cube. So, the specific gravity is the density of material relative to density of water, and that is a ratio of with no units, that is understood. Why density is important? Because consideration is material selection for a given application, but it is generally not the only property of interest. Okay. Now, strength to weight ratio is more important here in this case, which is tensile strength divided by the density. Okay. Thermal expansion similarly, density of a material is a function of temperature. In general, density decreases with the increasing of temperature, that we all know. Volume per unit weight increases with increasing temperature. Thermal expansion is the name for this effect of the temperature or the density, and this is measured by the coefficient of thermal expansion. Okay. And let us say this is coefficient of thermal expansion given by alpha. This is given by this formula. This is the change in length for a given temperature. All right. Here is the coefficient of thermal expansion, and L1, L2, these are the lengths corresponding to the respective the temperature. Let us say these are T2, this is at T1 temperature. So, this is these are the temperatures, and at this temperature the length is TL2 at temperature T2 and so on. Thermal expansion in manufacturing, this is used in the shrink fit. In the fits and tolerances we will discuss in more details. Part is heated to increase the size or cooled to decrease the size. This permits the insertion into the another part. Okay. So, the melting point is a pure element, is the temperature at which it transforms from solid to liquid state. So, this is just a reminder. Heat of fusion, it is the heat energy required at melting temperature to accomplish the transformation from solid to liquid. This is melting of metal alloys, melting of non-crystalline materials. These are the simple definitions which everybody knows that, and this is the specific volume versus the temperature shows. And importance of the melting in manufacturing, I already told you that this is in case of casting, this is in case of the plastic molding, and the thermal properties of the specific heat, thermal conductivity, and these properties relate to the storage and flow of heat within a substance. So, the rest of the materials in this series of discussion we will have it in our next session of discussion. Thank you very much for your attention.